everybody. Welcome back to the Climate Talks podcast. Climate's talking. I hope you're listening. My name is Sam Orndorff, coming back to you again right from the bottom of the dome, the Love Library Dome basement here in the Digital Humanities Center. And today I'm going to be talking to you about the atmosphere, the air. The atmosphere is a huge part, probably the part of the climate and the weather. I mean, when you really think about climate and climate change, that's kind of what you're thinking about, right? Is the atmosphere. So what are we doing today? We're really building on what we talked about previously when we discussed land, the sort of highs and lows, the topography, the unevenness of it in terms of how high up into the atmosphere it goes, and the low troughs and this particular shape of the continents relative to the oceans. So we're going to be tying in this sphere, the atmosphere, the air, in with the other spheres. So what are those spheres? Those are the lithosphere, referring to rocks and volcanoes and the cycle of rocks. That's the hydrosphere, that refers to all of the water, the fresh water, the lakes, the groundwater, the oceans, etc. Then there's also the biosphere, all living things that are really created out of these other spheres. And there is also, too, the cryosphere, which is the ice caps, the glaciers, and all of those things. We're still in the very end of the last ice age. And so all of these spheres interact. And when we talk about weather and we talk about climate, the atmosphere is probably what you're thinking of, right? And so just to say this, I know you might know this at this point, or maybe you don't, but the difference between the weather and climate is really just a matter of time, right? So weather tends to happen over the shorter time period, minutes, hours, days. And then the climate is the broader time scale of what happens in a particular place on planet Earth over a broader time. Not necessarily geologic time, but just the broad time of like hundreds of years, maybe. So climate is relatively stable, and the climate kind of tells you, given where you are in relative to latitude, if you're in the tropics, if you're way up on the poles, and given the time of the year, whether it's the seasons of the winter, like kind of where we are now in the Northern Hemisphere, it's March. So we're kind of ending the winter season. And all of those things will help you to identify not just what the climate is, but sort of help you predict the weather. Okay, so weather happens over a short time, climate happens over a broad time. And the reason that we can sort of tell these things, that scientists are able to understand the climate system, is because, for one thing, we've been keeping records for a very long time. And for another, the Earth system is a closed system. You know, give or take a little bit of margin of error. But what do I mean by that? Well, the Earth's system is a lot like when you talk about the conservation of matter. Like matter in the solar system cannot be created or destroyed, right? Same thing with water. Earth's water is sort of a closed system. Like you can't really add or take away water into the system. You can move it around, you can pollute it and fuck it up. We have a lot of practice doing that. It's the same thing with the atmosphere and how much energy it is getting from the sun. Okay, that's a really kind of a set amount. So that's what we're talking about with Earth's energy balance. Our planet is getting a ton of energy pumped into it every single day through solar radiation. It doesn't really change. So the way that the planet deals with that, I'm kind of personifying it, or sort of anthropomorphizing the planet, but I think it helps to think of it that way. And the way that the planet deals with all of this solar radiation is it redistributes it through different layers in the atmosphere and through wind and through interactions with water and air and land and air and the overall whole thing. So the Earth's energy balance is how we redistribute our energy, how we start to feel heat or cold or wind. It also turns into weather patterns, which I'll get to. But one thing you actually should know is that solar radiation, it can change it a little bit, just a little bit, okay? The sun goes through a little bit of cycles, like every maybe 10 years, it'll have these little bursts of energy where it's giving off a little bit of extra heat, extra radiation. Those are sort of stable around that 10 or 11 year cycle. Now, Earth's positioning does change too over geologic time, though. We're talking 10 to 100,000 year cycles. So Earth's orbit around the sun, its eccentricity, I love saying that, eccentricity, that'll change a little bit, and that changes climate. The Earth's axis, as I said, it's tilted on an axis about 23.5 degrees. That'll change a little bit. That's called obliquity. So that 23% might drop down to 22 or up to 24. And these are little changes, right? And the last little change in Earth's positioning is the direction of its axis. So the rotation is either pointed or not, and that's known as precession. Those are called the Milankovitch cycles. They're what you study if you're really looking deep into climate and you're a physical scientist or a climatologist trying to understand like ice ages, especially over deep geologic time. Those have been around in science for about 100 years. And those are known, those are givens, so they do shape our climate system over those cycles. But they are not causing or preventing or disproving climate change. Why? Because the composition of the atmosphere, okay? That is how we know that these cycles, the Earth's orbit, the Earth's axis, its angle, the direction that the axis is pointed, those things change. Earth's positions, it does a little wobble, does a little shake. But in general, we have a set climate system, and our atmosphere stays constant. But it does change with the burning of fossil fuels. It increases the CO2, which is increasing Earth's ability to absorb heat within the atmosphere that we're living in. All right? So the solar radiation stays constant, and it has to be handled. It has to be redistributed through all of these processes, these different spheres, the atmosphere, the hydrosphere, the biosphere, the lithosphere, and even the cryosphere. They are all interacting to redistribute Earth's heat. As they do that, they're creating weather. Okay, so one of the ways that Earth deals with solar radiation is that it's going to have this horizontal movement of air. What is that? That's just wind, right? That's the prevailing wind patterns that you feel. So if you are like me and you're in North America, you're going to have a pretty constant wind pattern of air moving from the west in the Pacific area, Pacific Ocean, and it's moving from the west to the east. That's the prevailing wind pattern at this latitude in this particular location on Earth. And there are other prevailing wind patterns in different spots, and we'll get to those. But there's another thing that Earth does in terms of just the movement of air, and that is it moves air vertically. It moves air up into different layers of the atmosphere. So what are we talking about with that? Well, basically, Earth's rotating, right? It's every 24 hours it does a full rotation. Believe it or not, Earth rotates really fast, especially at the poles. It rotates around 1,000 miles per hour. A little bit slower. It'll move a little bit slower around the tropics, though. So Earth is rotating, and as it does that, winds will happen because of the Coriolis effect, or the Coriolis force, and the conservation of angular momentum. So Earth is moving. It's sending its hot air from hot areas down to colder areas. It's sending its air through those prevailing patterns that are sort of constantly going horizontally. The other thing that it's doing, especially, is sending hot air up into the atmosphere. Okay, so understanding that the atmosphere goes up and that it has these sort of conveyor belts, and there's three major sort of chunks, there's three cells in this 3-cell model. Understanding that really helps you understand the basics of climatic patterns and atmospheric circulation. Okay, so let's start with the tropics. So in the there's this thing called the ITCZ, the Intertropical Convergence Zone, and that's just really like a fancy term for the fact that in the tropics. So we're talking like the Caribbean or Singapore, Sri Lanka, where else? Papua New Guinea, even places like Ecuador, although Ecuador is very, very high up in elevation, so it's a little bit different. Those are all countries in the tropics. And at that point on Earth's globe, it's getting the most solar radiation, right? In the tropics, around the equator, like there's not really seasons. You might have a dry season and a wet season, but in terms of like, oh, it's colder, it's the winter, like we have up here in the northern hemisphere sort of right now, they don't get that in the intertropical convergence zone in the tropics because they're constantly getting that high solar radiation all the time, right? That big band around the Earth's middle doesn't really matter if it's winter or not. It's getting a lot of high heat. That high heat that it's getting is heating up the oceans around there, okay? And when you have warm ocean water, that warm ocean water is really prone to evaporate. And then once it evaporates, it keeps moving up into the atmosphere, and then it condenses into clouds, and those clouds will then go on and typically rain. Okay, so that's why in the tropics, you're seeing like constant changing of weather. You're seeing a lot of rain very often, and then you also will get storms from time to time too. And so that's the first cell in the 3-cell model. So that's basically the Hadley cell. So it's getting low pressure, hot air that is then rising up, not horizontally, but up vertically. Eventually it hits a cap though, right? So it's causing weather patterns. It's interacting with the oceans around it. Some of that air is condensing into clouds and moving on into other areas. But when we talk about the vertical, looking at Earth vertically, it's really hard to describe. You should definitely Google 3-cell model. It's a very visual thing. But so I'm saying vertical to just describe that it's going up in the atmosphere. It is gaining in high pressure, and that high pressure belt is coming back down down vertically, back down onto Earth around the 30 degrees north and the 30 degrees south, where I have said multiple times, that's where you see most of Earth's deserts. They are high pressure, warm air, right? And then there's another cell, that's the Ferrel cell. That's that wind is constantly moving again, and it's recirculating like a conveyor belt again up to 60 degrees north. And then that's 60 degrees north is where the Ferrel cell and the polar cell meet each other. So check out the 3-cell model. It's a really good way to understand how prevailing winds and atmospheric layers work together. Okay? And so the key thing to remember there is that around the tropics, it's constantly warm. The ocean water is pretty warm. Ocean water that is warm will tend to create a turbulent weather, especially if it's low pressure, low atmospheric pressure. And then in other areas, so that's why you'll see the Caribbean's really warm, like the Red Sea is really warm just based on where it is geographically. But then there's those other ocean currents like we talked about where there's cold water that's moving south from, such as the California current that's moving south from the North Pole. Cold water is not as prone to evaporate and to turn into storms and turn into precipitation. So on a lot of the west coast of continents, you will typically see a lot of deserts right next to the ocean. That's pretty weird that you can have that, and it's actually really common. And you'll also see a lot of Mediterranean climates and those western sides of continents as well. And so those are a way of understanding that, okay, the coastal location is interacting with where it is on this 3-cell model, whether it's experiencing like constant high pressure or not, or low pressure. So low pressure would be in the tropics, high pressure would be around that 30 degrees north. And then, understanding how the atmosphere ties together the land, the water, and the air. And so there are different layers of the atmosphere. What I've been talking to you about has been the stratosphere and also the troposphere. And that is where pretty much all of Earth's weather happens within those. And that goes from Earth's surface all the way up to about 11 miles up. And so it's a little bit higher up. That layer is the troposphere layer of the atmosphere is a little bit higher up in the mid bands around the equator. And then up on the poles, so the North Pole and the South Pole, it's that layer of the atmosphere is a little bit thinner, about half as high up. The next layer of the atmosphere is the mesosphere. Then there's the thermosphere and the exosphere. And so all of those interactions between wind, between air and water, between whether it's the middle of the continent or the edge of the continent where it's a coast. And then also think about the shape too. That's going to the shape of the continents have a really big effect on that too. All of these things come together to show us what is the weather in a particular spot. It should be fairly predictable, right? If I just get a globe and just kind of throw it in the air and pick it up and let it land and point to a spot, it's probably going to be on the ocean. But if it's over land, if I know the latitude, right? If I know the season, and if I know the topography, I can get a pretty accurate picture of, well, what's the weather going to be today in that particular spot? Or if you're going on vacation, use that trick too. And see if you can kind of predict what is the weather at this random city in another spot of the world in a particular season at a particular time of day. And if you have been listening and following along and piecing these together, hopefully you can have some sense of what the weather would be there before you just go and Google it. Okay, so the atmosphere is tying all these things together to help us understand the climate and help us understand that there's these different layers to it and there's these different prevailing wind patterns. Air that's rising and then it's hitting the top of the troposphere. It can't really go past that, and then it's going to condense to form a cloud, and that cloud is going to move along in an air parcel. When an air parcel hits a big piece of land, such as a mountain, it's not going to go through the mountain, obviously, right? It's going to go up. It's going to keep going vertically in that atmosphere. And then so an air parcel, when it hits a big mountain, it rises as air rises, generally within the troposphere. As air rises, it cools off. And cold air can hold less moisture than warm air. So that cold air will then release all that moisture as precipitation on one side of a mountain, but also that air will keep moving. As it's moving, it's releasing moisture and precipitation and causing snowy frosted peaks, but it keeps moving and then it's dry and it's high pressure on the other side of those mountain chains. So we're starting to hopefully get a complete picture of why there are big dry stretches in areas that are surrounded by mountains. This will hopefully give you a picture as to why the tops of mountains are cold, like the Atlas Mountains, right? Or here, the Sierra Nevada mountains. Both of those mountain chains are covered in snow. They provide a lot of fresh drinking water as that snow melts throughout the year. And they're also surrounded by really hot deserts. So the elevation of the land really comes to have a big effect in the climate and the weather. Okay? The other thing you got to think about too, as I said, the temperature of the oceans is going to have a really big effect on the climate as well, because cool ocean water is just kind of like stubborn. Like it doesn't want to just evaporate because it's cold. It's cold water. It's going to keep on moving until it hits a warm current, and then at some point, that warm current is going to kind of prevail. And then the water sort of does the same thing where it'll move from warm to cold, and also it can also move from cold to warm. But what's happening there is in cold currents, they're not going to evaporate as easily as warm currents. So that's why a lot of like cold polar places like Alaska or like the tundra, like the northern reaches of the Eurasian continent, they don't get a ton of precipitation because their weather typically will have some snowfall, but not even then, really not that much. And so there's these cycles within the cycle of weather, within the cycle of the 3-cell model, and within these movements of parcels of air in the atmosphere, Within that, there's a really big phenomenon, or I should say, not big. It's expansive. It covers a large region, but it's significant, we'll say. So what is that? That is the El Nino-La Nina Southern Oscillation, or ENSO, ENSO. And basically, it can be kind of boring to talk about this. So essentially what's happening is in some parts of the Eastern Pacific, which is basically where we are here in San Diego and places like coastal Peru, in those waters, sometimes in the winter, it'll weirdly be warm. And so you'll see a little bit of extra rainfall and extra precipitation when that El Nino is happening. There's warm water in the Eastern Pacific. And La Nina is the opposite. There is warm water in the Western Pacific in places like Indonesia. And so it goes in these cycles. If you're really into climatology, you'll know a lot about that. But all that is basically to say that when we have cold water off the coast of the Pacific coast in the Western North America, that'll be sort of the norm, and that'll be associated with less rainfall, less precipitation. And they'll also be having warm water over there in like Southeast Asia, and those are both the norms. But those switch from time to time, depending on the El Nino and La Nina Southern Oscillation. So all of those are happening within this general norm of the atmosphere, how it works, how it redistributes air, how it redistributes heat, I should say. But the thing that I wanted to really nail down, and this is the part that's crazy, is that our atmosphere right now, I had to Google this, has 425 parts per million of CO2. And that's a lot. The last time that our atmosphere was composed of 425 parts per million CO2 was about 14 million years ago. So that is way before humans ever came along. That's like the time when volcanoes were like really popping off. The continents were slightly in different positions than they are now, although it was starting to get close to what we see now. And just life on Earth was radically different when the last time, I think it was the Cenozoic, the last time that the CO2 was so high. So high CO2, it's associated with those really active volcanic periods. It is also 100% unequivocally caused by the burning of fossil fuels. It's just part of the reaction that happens. When you burn coal, when you burn oil or natural gas to heat up some water, and that steam spins a turbine to either generate electricity or perform some other industrial function, maybe to run a car or to heat up a house for coal. What you get is you get heat. That's one of the byproducts, so that's good. You can use it. And you get pollution. You get CO2. You get some of this particulate matter as well. And we know that there's all kinds of like tracing and biomarkers and indicators that can say for sure the extra CO2 that's in there. Not only is it way higher than it was in the pre-industrial era, it is for sure from burning coal, oil, and natural gas and other fossil fuels. So the pre-industrial era, that was a time when people got around on horseback or by walking. They would burn wood for heat in their house or to cook or whatever, sure, but they're not burning it at an industrial scale, and they're not digging it up everywhere every chance they get. Right, so it was the pre-industrial era was just completely different period in human existence. And we still had fun back then. I mean, people might have died young in some cases, and medicine was not developed, but people still had fun, full lives. They kind of sat around together at night, and they couldn't watch Netflix, so they would just sing a song or, tell a story. But that's really, that's the crux of it, is that the composition of the atmosphere has really shifted. And it's shifted from burning fossil fuels, and that has everything to do with CO2. And so there's other things that the atmosphere is composed of. It's not just carbon dioxide. There's some water vapor in there. There's some nitrogen. There's some argon in there. There's quite a bit of dust that just happens, right? There's just dust moving around. Like the solar system is dust. The Milky Way is dust. We are dust composed from stars. There's some aerosols in the atmosphere as well. But when you look at those particular components that form up the atmosphere, then you start to see, okay, the last time we had so much CO2 in the atmosphere, Earth was basically a dramatically different place. Humans were probably not around then, definitely were not around then. Life, the ability to support life on planet Earth was dramatically different as well. And you also can start to see that there are things that are really dangerous to human health, just having them in the atmosphere, right? Like lead or ozone. So O3 is ozone, that oxygen layer, that oxygen molecule, I should say. That is atmosphere. O3 is atmosphere. And when you drive a traditional internal combustion engine car, it is letting out O3 at the surface level. That's terrible for your health. Okay, you don't want to be anywhere near a car that's idling, right? I mean, it's even in movies. They have, unfortunately, they have scenes in movies and shows where somebody runs a car in a garage on purpose to end their own life or something like that. But we're doing that all over the planet. We're doing it next to schools where little kids are with their little vulnerable bodies and their lungs that are just now getting a chance to experience the world and to breathe. And we're idling rows of cars there, spewing out CO2, spewing out O3 at the surface, just because that's the way we've done it for the last not even 100 years. So we really have to rethink the way we get around, the way we heat our homes and our schools and our buildings, the way we produce electricity. How are we producing it? How are we doing it? How is our food system producing CO2? What surface is it? What is the surface of a land? Is it a bog or a wetland, which are really good at sequestering carbon? Or is it just grass, which is horrible? It's not sequestering carbon really at all, right? So I just want to say all that to kind of tie it back to what's changed in geologic time, what's changed in the human time, in human history, and also to sort of point out that we're really lucky. The planet just kind of magically happened to support life. All of those long phases of great extinction events and those constant volcanoes like billions of years ago when Earth was just spewing out toxic gas. That's not all that different from the gas you get in fossil fuel industrial processes, but it was doing it in volcanoes, and that just kind of calmed down. The aquatic-based life forms started to produce oxygen through their metabolism, and the land-based organisms that were microorganisms started to become more and more complex, and those cellular beings started to work together instead of competing, and they formed more complex beings. And then eventually, those beings that survived the asteroid hitting the Yucatan, they went underground to survive that really bad extinction event. Well, we're coming into another extinction event just now. So when you have extra CO2 in the atmosphere, we know for sure extra CO2 increases heat. That's just what it does. And so the extra CO2 that's in there right now is going to for sure lead to a heating, at least 1.5 degrees heating globally on average since the pre-industrial time is almost a given for sure at this point. And they wanted it to be less. As I mentioned in the first episode, the international community really tried to get, okay, let's do whatever we can to lower our emissions, i.e. our pollution, and get that heating to just stop going up and have the average raise be not so bad. Now, it might not sound like a lot, 1.5 degrees, but as I said, it's going to keep going as we keep burning more and more fossil fuels. And if you had a fever, you would only be about 1 or 2 degrees above normal, but you're incredibly sick. So think about Earth like that. And if you want to read some really good examples of the international system and the grand scheme and how do we address this, how are scholars thinking about how we address this, and what is the logical conclusion of all these things that on paper sound great and the international community is acting like it's really solving the problem. 2 good books I recommend would be Climate Leviathan by Joel Wainwright and Jeff Mann, and The Future of Denial by Tad DeLay. And the atmosphere is something you should always think about. If you can ever do anything that reduces your overall pollution, if you can take transit, if you can walk instead of driving, if you can be more conscious of, how much energy you're using, if you can join any kind of movement to shut down fossil fuel production near you, there probably is something. There probably is a coal power plant that's burning coal to produce electricity somewhere near you, or it's shipping in coal from somewhere else, or oil or natural gas. These are all the things that we really have to get away from as a society, because the atmosphere is fragile. It is thin. If the Earth was equivalent to a basketball, the atmosphere is so thin that it would be roughly equivalent to just putting that basketball into like a pillowcase. That thinness of that pillowcase is equivalent to the thickness of the atmosphere. So it's a fragile system, but we're all so lucky that we get to inhabit this Earth that has just the perfect temperature for us. This is our home. This is the only place that we've ever known. And so when it comes to climate change, reducing our impact, fighting for environmental justice, like these are must wins. So I just want to leave you with that. As always, if you have a comment, a critique, if you want to tell me I'm wrong or I'm crazy, go ahead. Please do. Send me a question at climatetalksquestion@gmail.com. And that is going to be it for today. I hope you have a great day, and I will see you next time.